Yeah, it's plugged in, so you can advance the slide.
So just like everything my experience.
Far off.
Not putting a hole through my jacket. Just light, yeah. I'm just putting it in so the brush. It's great.
Oh, that's
It's this.
It's like the knife. Just checking. That's fine. A little bit careful. Okay. Everyone has coffee, so there's no sleeping now. All right, our next speaker is Valentin Taufour. Known him for quite a while, since he was working in the Campfield lab. We did an experiment together, remember? Yes. The Walker cell, right? Anyways, he's been a professor at UC. Please go ahead.
Thank you very much for giving me this opportunity. So yes, my talk is how to grow magnetic single crystals and then give it magnetism. I will repeat some of the things that Ryan already explained before about phase diagrams and so on, which is good because this is a school, so repetition helps learning. And you had coffee, so you are awake, but it's also the talk before lunch, and so I know what's in your mind. You want to have, is this working?
Or turn it on, maybe?
Turning on with some.
Oh, yeah, it's down this.
Right. So yeah, that's what's on your mind. So imagine, close your eyes, imagine you have like a bag of potato chips, and then you select very carefully the biggest one, the most beautiful one, and then you break it into pieces. Right? That's what we do in fact. We make a crystal, the most beautiful one, the biggest one, we polish it, we're very gentle with it, we select the best one, and then we put an enormous amount of pressure on it, we cool it down to extremely low temperatures, we bombard neutrons on them, you know, that kind of stuff. So that's also what we do in my group, and we study materials, right? So quantum materials. So what I've mostly worked on are all of those topics here, strongly correlated systems, superconductors, magnetism, topological materials. And in fact, they are not separated like this into little boxes. Often they're connected to each other, and they're connected by the materials themselves, because one material can show properties that belongs to several of those topics, right? One material can be magnetic and superconducting at the same time, a topological superconductor, and whatnot. And as it was already discussed today, before you can study them, you need to make materials, and so you're going to use various techniques to grow materials. So I will talk about solution growth and Czochralski technique, but there are other methods, vapor transport, Bridgman, and so on. Then you're going to use the characterization tools, structural characterization, magnetic characterization. You're going to use, for example, a cryostat and MPMS. You're going to put contact electrical contacts and then measure transport measurements, resistivity, or Hall effect. Again, maybe you have a cryostat like a PPMS to do these types of measurements. And then you want to tune the properties. You want to modify the properties that you have in your material. And so you can do this by changing the temperature. You can go back to the synthesis and change the chemical composition. You can use high magnetic field. And the topic of this school, you can use high pressure also to change the properties. Again, all of this you can do, but it starts with a sample, right? So you have to make your material first before you can do any of these other fancy and interesting studies, right? Like I tell to my students, no samples, no data, no data, no results, no results, no PhD. I want to start there. And so I'm going to tell you a story that my postdoc advisor, Paul Canfield, told me. So this is the story by Paul Canfield. So it goes like this. Once upon a time, there was a nice single crystal that got dropped and broken by a hurried student. And so there was great anger in the lab. And the advisor was very angry and says, do you have any idea where single crystals come from? And yes, said the students, they come from FedEx. All right, so of course, this is not the correct answer. And the point of this school is that you can learn the proper reply, where crystals come from. And so we're gonna decide this. So like I was said before you grow a material, you need to know what you want to do. You need to, you have this step sync here where you need to decide what you want to do. And then you need also to think how you're going to do it, okay? How you're going to make this crystal that you want to study. And so we use the maps, right? We use the maps that were introduced earlier today, the binary or ternary compositional phase diagrams that gives you the different phases that you have as a function of temperature and composition. All right? So they are the equivalent of the geographic maps if you decide to go on a trip. So let's say at random, from my accent, that I want to go to France. Okay? So then I'm going to say, well, is it bordered with the ocean? Because if it is, then I can go by boat. If it is not, then maybe there is an airport. If there is, then maybe I can go by plane, and so on and so forth, right? So we use these binary phase diagrams in the same way, okay? So we have regions that have liquids. So then if there is access from liquid, maybe I can do solution growth. But if there is no access from liquid, then I need to do something else. Is there a good transport agent? Yes, maybe I can do vapor transport, or no, then I try something else, right? We use the maps to decide the synthesis technique. It's an actual science, right? A lot of people are going to tell you that it's black magic. There are some parameters we don't control, but there are a lot of things that we can gather scientifically by reading the binary or the ternary compositional phase diagrams, right? And so I'm going to be able to go fast because Ryan already introduced how to read them, but they are all available online at this website, ASM International, and this is the picture of the headquarters they have in Ohio, which has like, I've never been there, but the buildings, I found the picture online, looks really cool with this dome of graphene on top. So this is where the phase diagram I'll show you are from that website. So I take a different one. I take this one, silver. So 100% silver here, 100% barium here, and then this axis is temperature. And so you see this big region on top of liquid. If you go to high temperature, usually that's what you get. And as I mentioned already, you have the first thing you can look is like these lines here, that boundary between liquid and the white regions are called liquidus line. And so, for example, this one here is the liquidus line for barium silver. Above that line, you have a liquid. Below that line, you have two phases, a liquid and barium silver solid. Okay? So that's very useful for solution growth in this case of barium silver. You also see something else here. You see a width of formation. So barium silver 5 has, it exists in a variety of chemical composition. So it's not exactly 1,5. It can be like 5.1 or a little variation here. By contrast, other compounds here, they are line compounds, so they only exist at this one composition, barium silver 2, barium silver, barium 3, silver 2, line compounds. What else you can see on this phase diagram? Or the way, so you have those maximums here. So barium silver 5 and barium silver 2, they have a maximum here, which we call a congruently melting material. So these materials, you warm them up and they melt. Like most materials we know and think of in real life, they are congruent and they melt like this. But in fact, many materials are not like this. Some of them decompose. And so there are examples here too. Barium silver, you warm it up, it doesn't melt, it decomposes into a solid and a liquid, okay? Barium 3, silver 2, same thing, at 360 degrees Celsius, it will decompose into a solid and a liquid. The liquid composition is given by this line, so at the decomposition it's about 71% barium, 29% silver, okay? All this information you gather from reading this type of phase diagrams. And then finally, you have these eutectic points, which are the minimum in the liquid region. Okay, so the big liquid region here, and you have a minimum here, another local minimum here, and a local minimum here. So those are the eutectics. They are the lowest melting compositions of your liquid. And so sometimes, and so these eutectics are very useful if you want to do solution growth. You want to locate them very fast. An example, there was a question earlier about this also. An example of this is salt, right? You put salt in water and you know that it decreases the melting point of water. And this is useful, for example, to reduce ice on the roads, right? You put salt so that you don't have ice on the roads. You can add more salt and then you decrease it more, but eventually at minus 21 degrees Celsius or minus 6 Fahrenheit, then it's going to freeze no matter what, no matter how much salt you put in there, okay? So that is the eutectic point. That is the lowest melting you can get. Lowest melting temperature for here salty water. Sometimes they can be very deep. So for example, this one is the phase diagram between gold and silicon. Both of those materials, they melt above 1000 degrees, but the mixture of them at the eutectic composition melts at 360 degrees. So it's very deep eutectic. Another example of this is boron platinum. Boron on this side here melts at 2000 degrees. Platinum melts at 1700 degrees and more. But there are regions here that are liquid down to 790 degrees Celsius. So very deep eutectic gives you a lot of temperature range of liquid so that you can design your solution growth, your synthesis into a solution. So enough talking, let's grow something. And so let's grow manganese bismuth. Why you want to grow manganese bismuth? It's a magnet. It's a magnet at room temperature. It has a good anisotropy. And so it could be useful, for example, as a rare earth-free permanent magnet. Okay, there are people who are interested in this. Toyota, for example, a couple of years ago had a project on studying manganese bismuth as a potential magnet for the electrical motors. So if you want to grow a single crystal of manganese bismuth, and you have this phase diagram here, so again, temperature here, pure manganese is on this side, and then pure bismuth is on this side, and manganese bismuth is here. It doesn't melt congruently, it decomposes into this other solid here, manganese bismuth 1.08, and then a liquid. So if you mix manganese and bismuth 50-50, then you're not going to, and let it cool down. So say you go to high temperature, and then cool down, you're not going to get pure manganese bismuth, you're going to first cross this liquidus line here and get solid manganese. Then you're going to get this high temperature phase of manganese bismuth, manganese 1.08 bismuth. Then you're going to get manganese bismuth, and then you're going to get pure bismuth. You're going to get 4 different phases instead of one nice manganese bismuth, right? But instead, the trick is to work in excess of bismuth. So you use this phase diagram to figure out what amount of bismuth you want to use. And so you see that starting from about 90% bismuth, you have this liquidus axis here that separates the liquid from this region here, which is manganese bismuth plus liquid, okay? And so if you start here and you go to the liquid region where the cross here, you have a lot of bismuth, 90% bismuth, which is in blue here, and then 10% manganese, which is in red. And then you cool down, and just below this liquidus line, now you have 2 phases. So you have the solid manganese bismuth that started to form somewhere, and then you have the rest of the liquid. The liquid then is more and more rich in bismuth, and the composition of the liquid is represented by this arrow here. Now you keep cooling down, your crystal grows bigger and bigger, and the rate of the crystal growth will be essentially the rate of your cooling. So you have good control. If you control your temperature, you control your growth rate, which is good. And then if you keep cooling down, you're going to reach this eutectic here, and then everything's going to freeze. And sometimes that's okay, you do that, but if you really just want to have the crystals, then you're going to decant to separate the liquid from the crystal, okay? So that's where, as was described earlier, you're going to use a centrifuge or something, some kind of filter, and then you get your crystals out of the crucible, separated from the liquid, okay? So that's an example of solution growth, and but that was still on paper, theoretical, right? And now let's do it. Let's do it for real. So how do you do this? So you're going to go to your cabinet, and then and take, you know, manganese and bismuth. That's what you need. You're going to go to the scale, take the masses, measure the masses, and get them into the correct amount. Okay, so we want 90% bismuth, 10% manganese, atomic percent. So you do your little chemistry. And then you're going to put this into the crucible. Then if you're going to use a centrifuge, you want to also plan for the separation step. So you put this frit and a catch crucible that is empty, that is going to catch the excess liquid at the end. And because manganese reacts with oxygen, you have to seal the whole thing into an ampule. So you're going to use a torch to seal your material into an ampule. So I think the next one is this. So going to use a torch. You want to have good control on the position of your silica. So you may want to use gloves, but then that's not so good. So you have bare finger is okay. Why is that? Because silica is such a poor thermal conductor. it can be so hot that it's liquid at the center here, but still not so hot on the edges. And then you neck it down, you reduce the diameter. After that, you're going to evacuate the air, replace it with either vacuum, nothing, or with an inert gas like argon, and then you have your sealed ampule. That's it. Then the rest is kind of easy. You put it in a furnace. So in my lab, for example, furnaces have names. So that furnace name is Snowy, like the little dog. And then you put it standing up because it's going to get liquid. Right? So we use another bigger crucible here to keep the ampule standing up. Then you go through your temperature profile. And then if you want to separate the liquid using a centrifuge, then you're going to have to take it when it's still hot enough to be liquid and dump it into the centrifuge. And so that is a little more scary. So essentially you have your hot furnace here, and you're going to wear gloves, face shield, the whole safety equipment, then tongs, and you're going to grab the thing at inside the hot furnace. And so don't do this at home, okay? This is done by a professional. She is an undergraduate student with 1 week of experience. Right? And then we put this into the centrifuge here, spin very fast so that we have higher acceleration to push the liquid through the frit. And the reason we have to do this is because bismuth is very viscous, much more than, say, water or something. Most metals have, liquid metals have high viscosity, so just like flip it upside down, it's not going to work out for you, right? So you want to really push it through the frit with the centrifuge. Okay, and then you get your crystals, and this technique is very useful and very versatile. You can grow a lot of materials with it. So manganese bismuth look like this, some other materials, iron-based superconductors, some fancy magnet. This one is a topological superconductor. You can grow many different kinds of material with this method. All right, and so in my case, so yeah, I don't have time to discuss all of the other things that you have behind solution growth. You have, you know, more complex phase diagrams, kinetic problems, choice of crucibles, ternaries, I didn't say anything about that, metastable phases, vapor pressure problems, then, you know, explosions, all kinds of other things that, of course, some of them will be covered in this workshop, but in here I will move on to next part. But yeah, in my case, I was lucky to use this method for a lot of different kinds of materials, and that gave me exposure to a lot of different types of physics. Okay, so in this particular case, you know, iron-based superconductors, new ferromagnets, new superconductors, quantum criticality, all kinds of different physics comes from those materials. Now, another one. Let's say you want to grow uranium germanium-2. That's another magnet. That one is interesting because under pressure, it also becomes superconducting. So it's like the first compound that shows the coexistence of superconductivity and ferromagnetism. So if you want to study that, you're going to need to make crystals of uranium germanium-2. So uranium here 100% on this side, germanium on this side. Uranium germanium-2 is this line compound here over there. So you see that we have very little liquidous access, and it's at very high temperature. So solution growth not so trivial here. It's possible, but you need more information to design it. On the other hand, you see also that it's congruently melting. So you have this maximum here. So it directly melts into a homogeneous liquid. And so that tells us that you could use something else, which is, for example, the Czochralski technique or the Bridgman method or floating zone techniques that are working directly from the melt, solidification from the melt. So the Czochralski process is what works well for uranium germanium-2. The way it works is you make a liquid, again at high temperature, and then you're going to put a seed into that liquid. So the seed is typically a little colder than the liquid, so the material is going to crystallize, solidify on your seed, and then you pull vertically like this your seed, so and then you get a big, large single crystal of your material. So that is in fact the technique that is used to grow silicon, pure silicon single crystals, out of which silicon wafers are cut and then printed circuit are printed. So in this case, they grow these massive, very tall single crystals of silicon. Of course, for research, we do this at a smaller scale, but we explore a lot of different materials. And so this name comes from the Polish scientist who discovered this method, Jan Szokalski. He discovered this technique in 1918. He discovered it by accident. Okay, he was taking notes. There was a crucible of molten material next to his desk. He was still using feather to take notes at the time, and he wanted to put it in ink to refill. And then he mistakenly put it into his molten metal, realized this mistake, pulled very fast, and then there was a crystal. Okay, that's, he was working late, that's what you should do. Late and tired. Making mistakes. All right. So as was mentioned also by Ryan, you can use various ways to melt your material: resistive heating, arc furnaces, or induction heating. But the principle of pooling is the same. So it's all called Szokalski technique anyway. So in the case of uranium germanium-2, I used an arc furnace. So you create a arc discharge, electric arc discharge, and so you create an argon plasma. So the plasma is really hot. So that's why you can melt anything. In fact, you can melt the tip that created the plasma, and you can melt the entire furnace. Okay, so the entire furnace has to be water cooled if you don't want to destroy it from itself. So everything is water cooled except for the material you're making, which are directly in contact with the plasma. And so then they melt, you get a ball of liquid, and then you start pooling your crystals. So this is like a large crystal here that is being pooled of uranium germanium-2. And maybe these pictures are familiar to you because they made it on the cover of this very nice book that was written by, edited by the organizers of this workshop, which I also strongly recommend if you want to learn about synthesis and exploration in quantum materials. So enough talking again. How do you do this in reality? So Ryan already showed the video of the melting with the arc furnace. So you weigh your materials again, selection, weighing, then you use the arc melting, and then you get a ball of a polycrystal. You want this to be homogeneous, so you might flip it a couple times and then arc melt again to get a homogeneous polycrystal at the composition that you want. So uranium and germanium-2, right? You start from uranium, germanium, you melt them, mix them well, you get uranium, germanium-2. The only problem is it's not a single crystal yet, it's just a polycrystal. Then you use the Szokalski technique pooling. And so the first time you don't have a seed, so you're going to use something else. So typically you can use a tungsten tip. So you use a tip here that you dump into the molten ball of uranium germanium-2 or your liquid, and then you start pooling. So here you're going to get a crystal of uranium germanium-2. The second time around, you can use that as the seed. So this one, in this case, I used that piece. I oriented it along a specific axis. So that's why it's tilted here. And then I grow a crystal down here with that exact direction that I wanted. Okay, why you want to do this? Maybe it grows better quality this way, or maybe you want to do a neutron experiment and you want a large crystal in a certain direction. You're going to do that. Now, a couple more details. Initially, once you nucleated crystals on your tip or on your seed, typically you're going to increase the power of the furnace to make it more liquid, so more liquid, less solid. That will essentially reduce the diameter here, reduce the diameter of your crystal. And the reason you want to do this is because initially you have a lot of different grains, and you want to sort of reduce the number of grains up until you have only one grain, okay? Usually you don't have access to this picture, this is a cartoon anyway, so you sort of guess that if you reduce it, you're more likely to have just fewer grains. And then once you think you have one grain, then you start decreasing the power again, and then you grow the diameter, so you make your crystal bigger. Okay? Even for silicon, they still do this. Okay? They still use the same technique. Then you grow your crystal. At the end, you also do increase the power to make a nice tail here where you reduce the diameter progressively. Okay? Why you want to do this? To avoid thermal shock. When you're going to detach your material from the heat source, it will cool down very fast, and sometimes it can be too brittle on your material, and sometimes they can break, okay, or at least they can have a lot of strain in them. So there are examples of systems that breaks a lot, and so you end up with the crystal falling back down into the liquid, and then your day is ruined. So you don't want to do that. So you want to do a nice tail at the end to avoid this effect. And then, so again, in my case, I was mostly using this to grow uranium compounds, uranium returning to silicon 2, uranium cobalt germanium, uranium germanium 2. Lots of interesting materials. That gave me access, again, to a lot of different physics, heavy fermions, quantum oscillations, hidden order, wing structure phase diagrams, and so on and so forth, coexistence of ferromagnetism and superconductivity. And all right, so one more example. How would you grow manganese boron 2, MgB2? Magnesium, yeah. Oh, I knew something was wrong, but magnesium boron 2. So this phase diagram is here, pure magnesium here, boron here, MgB2 is here, and this is a case which we haven't discussed yet, which has gases. Okay, so we don't have liquid anywhere. Oh yeah, we have liquid just here, liquid magnesium, but then it becomes a gas already here, and then MgB2 is not even melting yet. Okay, so how do you handle that kind of thing? It's not congruent, it's not, it doesn't have a liquidus access, so you have to find another way, right? So for example, vapor transport, or a third non-self flux, a third flux, or something like this, right? So you're going to have to be creative. So, but because this is the topic of the school, pressure, you can also use pressure. Now, these phase diagrams, one thing to realize is that they are often thermodynamic phase diagrams, so they represent phases, stable phases at ambient pressure or vacuum even, depending how they were determined. So under pressure, they're going to change. You already know that if you apply pressure, you're changing the melting point of ice, for example. you're also changing the boiling point of water. Same thing for all of these phase diagrams, they're going to change with pressure. And so this is the phase diagram, how it changes. If instead of 1 bar, you have 2 gigapascal. All right? So it's completely different. Now, compounds are melting. And now, MGB2 has a nice liquidus line. And so now you say, well, now I can use solution growth to grow crystals of MGB2. All I will want to use is an excess magnesium, so I'm going to go here and then use that liquidus line here to grow single crystal. All of this inside a type of furnace that Wei described earlier, like a Walker system or anything I can give you, like 2 gigapascal, will do. And then you can get crystals of MGB2, hexagonal, nice little crystals. Again, I don't have time to talk about all of this, but if you want to know more, there are nice books. Again, the same book mentioned earlier has a chapter on this detailed example I detailed in this book. And there are other methods that I don't have time to talk about: electrochemical synthesis, floating zone technique, chemical transport, bridgement method, and so on and so forth. But I want to now ask you a question. Why did I explain to you all of those tricks? Why did the other speakers already give you all of those tricks? Why do we have this school to train you into making new materials, how to synthesize them, and so on, right? So, how many compounds, inorganic compounds, have been discovered so far? Any idea? Any wild guess? 200,000? More? Less? Less? Much less?
No.
No? Pretty good? Like a little bit less? So I counted them for you. Actually, I didn't, right? Chemists did that for us, ICSD. So this is the 90,000 is the correct answer. 90,000 started as soon as we could diffract and distinguish different structures. So in 1911, diffraction, Dawei diffraction, and then we have this nice curve here that shows, I'm only showing the stoichiometric compounds, okay? So not the alloys, not the iron 0.1, iron 0.2, iron 0.3, I ignore that, okay? And so we have all of these. That's about 4 per day, okay? Every day, today, there will be 4 new compounds. Tomorrow, 4 new compounds. Christmas Day, same thing, no break, all right? It's like never stopping. You can even analyze this a little more. We don't discover binaries very much. Most of the time, those compounds are going to be ternaries or quaternaries. 3 out of 4 are going to be that, okay? The binary curve is in orange here. It's already like saturated. In fact, the ternary curve is kind of already past the inflection also, but still, I don't know where it's going, but it's going to go high. And then quaternary is barely started, and all the other ones barely started. Okay? Now, I even had fun and look at which countries are doing this. Okay? So, used to be that USA was the best in the 60s. France also used to be good. Nowadays, Germany, USA, and then look at this curve. China, back in 2000, almost nothing. And now, there are a huge slope. In fact, if you include alloys, then they were already above everyone else in 2015. Okay, so today, for sure, they are above all of the other countries. This is about pressure. So you also have specific compounds that exist only under pressure. Of course, there are way fewer of them that are discovered. It's much harder. There are about 2,500 known phases that are considered high pressure phases. That's about 66 per year, so that's about 1 per week, a little more than 1 per week shows up on average in recent years, since 2005. Okay, and then once again, you can look at it by countries. In this case, US is a good country. And then Germany and Japan. And then China, again, very high kickoff here, rapid increase for materials discovered in China. Okay, so the thing about all of those compounds, so whether they're done under pressure or not, you know, we have these like 90,000 materials, and if you had to guess how many of them have been well studied, what would you say? No idea, right? This one is harder, right? Maybe it's 1%, maybe it's 50%. So we did recently with my group, we did a study that kind of can give us a hint. So we decided to look at all of the cobalt compounds because we were looking for new ferromagnets. And so there are 13,000 reported cobalt compounds. Some are non-stoichiometric, so there might be alloys or stuff like this, and some are stoichiometric. If you look only at the stoichiometric ones, then you have 6,000 of them. Sorry, about 5,000 stoichiometric compounds. And then we look at their properties. A lot of them are ferromagnetic. That's normal for cobalt. Cobalt compounds, cobalt itself is a ferromagnet at very high temperature. Some are anti-ferromagnets, and then some are magnetic and superconducting, or superconducting itself. But look at this. More than 3/4 of them have no known ordering, and I write this, but it's mostly no studies of magnetic properties. All right? They have cobalt in them, so you'd expect them to be magnetic, a lot of them. And there's pretty much nothing. No studies of this. So 3/4 for cobalt compounds. So out of those 90,000 materials, we have a lot of room for discoveries, right? So in this example here, if you take the cobalt compounds, right, and so you take any of those, you'd say, well, I have a high chance of them to be ferromagnet. Okay, so if you want to discover a ferromagnetic compound, you want to look into them, and very likely you're going to find ferromagnetic compound. That's what we did in this paper. We also described how to refine that search, looking at the cobalt content exactly, the structural parameters, and so on. And so that's why we do this. We need your help. I'm not going to be able to do it, and JP is not going to be able to do it. You know, no, we cannot do it, right? So we need people like you to accelerate this, make those materials, and then be able to study their properties, right? Because most of them, no one has looked at them besides just knowing the crystal structure. Question?
Can you tell us how you did this study? Did you do it by hand, or?
Yes, so it's a whole new talk essentially that I don't have here, but initially we started by hand, so looking at papers. So you take a compound, you go on SciFinder, Web of Science, you know, the old way, and you extract the information you're looking for. So in our case, for example, we looked at Curie temperatures and these kind of things. But then once you have this, you can use an AI to do this, right? ChatGPT can read the papers, right? So it just needs to be trained. So you can also train, once you have PDFs and manually extracted information, you can train an AI to do that for you, and you can speed up the database build up, okay? So that's different from most of the databases that are online, because most of them are theoretical, right? So they wrote a code that does some kind of calculation, put it on a website. That's completely different from taking known data that are hidden in literature, right? which is what we did here. So conclusion so far, how do you grow a magnetic single crystals and kill its magnetic? So I have only talked about growing materials. So you see that quantum matter physics starts with crystal growth, that there are many techniques, not just one technique that works for every material. And then there is huge potential for new discoveries, all right? There are lots of materials they've already been discovered, but they haven't been studied in the sense of physical properties. So in the remaining part, I want to move on to, now that I have this nice, potato chips, and then I break it, right? So I break my magnetic properties. So there are a picture here, because I'm not just obsessed with chips, I'm also obsessed with coffee. So if you want to understand how a coffee machine works, then you take it into all kind of pieces, you completely break it, and then you put it back together, and then you know how it works. Okay? So we do this for magnetism. So what happens if you suppress magnetism? So you can do it with pressure, you can do it with chemical substitutions, you can do it with magnetic field. What happens? So you get something like this. You get a phase diagram that's going to look like this, where temperature is one axis, and then this can be pressure or any kind of parameter that you're going to use. So you're going to suppress the magnetic transition, so from paramagnetic to ferromagnetic, and you're going to suppress it eventually completely at what we call a quantum critical point. Okay? So it's a phase transition that happens at 0 temperature if you tune your materials along this line here. Now, did people do this? Yes. It took actually a long time before we can find such an example. It was only found in 2019 with this material, cerium, rhodium-6, germanium-4, where you can take pressure and suppress the ferromagnetic order and reach what we call a quantum critical point. At least people believe there is a quantum critical point there. There was no new phases, no superconductivity that were observed, but there were new properties such as non-Fermi liquid properties that were observed here, strength behavior in transport and heat capacity and so on. Why it took so long to find this is because most of the time when you suppress magnetism, that's not what happened. Something else happens. So, for example, I mentioned uranium-germanium-2 earlier, and I'm going to also add another compound, zirconium zinc-2. These two materials are ferromagnets. When you apply pressure, you can suppress the transition temperature, so you suppress magnetism, but then all of a sudden, the transition disappears abruptly like this. So, in fact, what happens is that in this phase diagram, there is what we call a tri-critical point, where the transition changes from second order to first order. So it starts to have latent heat here, which it doesn't have latent heat here. Okay? And then due to a thermodynamic relation called Clapeyron relation, it disappears abruptly at T equals 0. So this tri-critical point is at about 3 Kelvin in zirconium zinc-2, it's at about 25 Kelvin in uranium-germanium-2. So then we don't have a quantum critical point. But quantum criticality is still, in this system, it is still there, but you need to go in a third dimension to see it. And this third dimension is magnetic field. So now I'm showing three-dimensional phase diagram. You have temperature, pressure, this is uranium-germanium-2 again, and now this axis here is magnetic field. So if you go back to the tri-critical point, where it changes to first order, you can track this tri-critical point on the field, and you see this new line here. It is symmetric with respect to positive field or negative field, and it forms this shape of phase diagram, which we call a wing structure phase diagram. And this new line here goes to lower and lower temperature, and so if it reaches 0 Kelvin, then you have quantum criticality. We call this quantum wing critical point, or a marginal quantum critical point. And this was observed in uranium-germanium-2. It was observed also in zirconium zinc-2. Same thing, except the wings are much smaller. This is at 3 Kelvin, and this is at a lower field. And it was observed in other materials, uranium, rhodium, germanium. also has these wings, and then other compounds, manganese silicide, uranium, cobalt, aluminum, and so on. So that's more common. And you will get those wings and this first order transition for many reasons. And theorists have started to look at this. So there can be coupling with the lattice, magnetic and elastic coupling. You can have peaks in the density of states or singularities of your Fermi surface. Or a last possibility is that those are all metal systems and you have particle hole excitations. And those particle hole excitations, they couple to the lattice, to the magnetization, and you can get a first order transition in this case. Because these have long wavelength correlations, they have a small wave vector Q. And so that led to another possibility, which is that those effects are so big that you get a new phase that has a small wave vector Q, for example, a helical order or spin density wave or any kind of like anti-ferromagnetic like phases. So you have ferromagnetic region and anti-ferromagnetic region. Now I already mentioned two examples of this case on the left, zirconium-2, uranium-germanium-2, and then an example of the case on the right is lanthanum chromium-germanium-3. So ferromagnetic region, you suppress it with pressure, and then you get this region here of anti-ferromagnetic phase. There are other examples of materials where this happens. Now in this case, same thing, when you apply field, you might recover quantum criticality. So you have a first order transition, not from ferro to para, but from ferro to anti-ferro. But when you apply field, this transition also can be suppressed here. So you have this new line, same thing as the wings. So you get to very high field with the possibility of having a quantum wing critical point. And so I'm going to show you this phase diagram again, but just the bottom, the t equals 0 plane. So the plane at the bottom here. So it looks like this. You have these lines of wings here that terminate at quantum wing critical point, and then the green region is the anti-ferromagnetic region. Then the ferromagnetic plane is here, and this is field and pressure. So the theory by Belitz and Kirkpatrick and so on, they predict that if you reduce the quantum fluctuations, then those wings are going to get smaller. So eventually they might terminate within the region of anti-ferromagnetism. And then you have a new type of quantum critical point, which we call a quantum tri-critical point. Okay, so that one has ferro and anti-ferro diverging fluctuations. And there is a case like this where you even don't have that at all with lower quantum fluctuations. And so we found a case of this intermediate situation here, which is cerium, titanium, germanium-3. So same thing, ferro, anti-ferro, and then the wing is smaller and terminates within the green region. So it has a quantum tri-critical point. The problem is to study this is at 5 gigapascal, low temperature, it's very high, very difficult to study. And so we looked for another material. First we thought, let's take the same material and dope it and see if we can do the same as pressure. So we tried this. We tried, so pressure here, vanadium substitution, but we got a completely different phase diagram. So in this case, ferro and anti-ferro regions are separated. So we need to find another system. And so this is where you go back to the sync step, right? We have all of those materials. How do you find the system that might have this quantum tri-critical point? So we could look at cerium compounds, uranium compounds. Those are materials that typically have magnetism that you can suppress. They're heavy fermion compounds. You can also look at iron compounds. We know iron-based superconductors have magnetism that can be suppressed, essentially cuprates and nickelates and so on. So we decided to look at chromium. So if you look at chromium and you say, I want compounds that have chromium only, no iron, no other magnetic elements, no cerium and so on, then you're down to 600 compounds. Then you may want to say, I want to have an isotropy or something like that. So you choose tetragonal structures or hexagonal structures. You're down to 300-ish compounds. Once again, you see most of them not studied, but some of them are ferromagnetic. So in this project, we're interested in a ferromagnet that we can suppress. So we only have 19 compounds to look at. One of them is the one I already discussed. So we know we're on a good track in terms of down selection. And so we pick another one of those 19. We can do band structure calculation to help us distinguish. So we pick lanthanum, chromium, antimony 3. And long story short, this is the phase diagram we got. Same thing, ferromagnetic, anti-ferromagnetic. A nice line that we can track the quantum tricritical point. But instead of reaching the quantum tricritical point here, what we found is another dome of a new phase. And so that's often what happens when you track quantum criticality, you get new phases. And so this is conclusion of my talk. The second part here, looking at suppressing magnetism, you see that quantum criticality can come in various flavors, many kinds of different quantum criticality. So quantum wing critical points, quantum tri-critical points, and then new phases can show up near any of them, but also in particular quantum tri-critical points. And so again, you can assist this type of discoveries by theoretical calculation, databases, material informatics, which is kind of what I was showing you with the down selection process. All right, thank you for your attention, and then I will welcome your questions.
Okay, time for questions. Yes.
What would be like a typical pull speed for those for the Wilson's crystals? Like how long does it take?
Oh, the rate, the pulling rate, yeah. So it's like in millimeters per hour, or yeah, a couple millimeters per hour. So the crystals I showed, they were like what, 7 centimeters-ish long. So those took a whole day. Yeah, so it's actually pretty fast compared to other techniques that take a week or 2 weeks or sometimes more. But it's slow in
Yeah.
So Tchaikovsky was lucky somehow.
So in fact, Tchaikovsky pulled it and it grew very fast. Maybe it was not a very good
single crystal.
Yeah, it was not a very good single crystal, but it's interesting because if you pull too fast, then it doesn't, it's going to detach from the melt. So then you don't grow your crystal. And Tchaikovsky's patent is actually on a new method to measure the rate of growth, because you find the limit where it stopped growing because you're pulling too fast. So that was the patent of Tchaikovsky, in fact.
Questions?
How is the magnetism suppressed in a ferromagnetic material with pressure?
Why is it suppressed?
In a ferromagnetic material.
Yeah, in a ferromagnetic materials, why is the magnetism suppressed under pressure? A very good question. So there are many possible explanations. So one of them is in metals, you essentially delocalize the electrons when you apply pressure because you make atoms closer, so the orbitals overlap more, so they form more of a metal, right? So things tend to become more metallic. And magnetism usually needs local moments, so electrons are more closer to the atom and less delocalized. So that'd be like the number one reason why pressure, tends to suppress magnetism. That works also for antiferromagnets, but yeah.
And it doesn't always go down.
Yeah, that's why. Yeah, it's more complex. Yeah, it sometimes goes up. Uranium, rhodium, germanium, I mentioned, it goes up. Right? So in that case, you can use another parameter like field to suppress the magnetism.
General definition of a quantum bit component. How many points do you have to specify? Define a quantum bit component.
Quantum critical point is when you have a second order transition, so a transition that doesn't have latent heat. That's like what is a second order transition. So that means no discontinuity in volume, no discontinuity in entropy, and no discontinuity in magnetization. Okay, so it's a kink, but not discontinuity. So that type of transition is called second order, and then you want that to happen at 0 Kelvin, and that's a quantum critical point. If it's not, if it doesn't stay second order, if let's say there is latent heat that happens, like in those materials, then we call it, it's not critical, because one thing about second order transition is that they have, they have a critical behavior, so the coherence length diverges across the entire material. That doesn't happen in cases where you have a first order transition. So they are not critical, so you should not call it a quantum critical point. You should call it a quantum phase transition. Quantum phase transition is just generic. It englobes like all types of transitions.
Sometimes I see people getting it not at 0. And how far can it stay?
How close you can be from 0 to say it? Yeah, that's a good point. So that's a very good question, in fact. So remember this, oops, going wrong way. Almost here. So zirconium zinc 2, for many, many years, it was considered to be a classical example of quantum phase transition, of quantum critical point. Because if you don't measure below 3 Kelvin, then you suppress it and then you don't see the transition anymore, right? So then you say, well, great, I found a quantum critical point. But people went down to lower temperatures, and then they found that actually it disappears abruptly. So it's not a quantum critical point, it's a quantum phase transition. It's a first order transition. Okay, and then they found wings and everything that goes with first order transition. So yeah, it's a matter of like how much lower, we can never reach 0 Kelvin, so wherever you start, you're gonna say, well, at least down to there, it's a second order transition, so looks like I have a quantum critical point. But you cannot be sure, right? So that's like almost a philosophical question in the end. Maybe every material never has a quantum critical point, because we can always say, well, you gotta cool down lower.
Any final question? 2 questions, yeah, go ahead.
So these phase diagrams constructed by the radical evolution or
Experiment. These are, well, the one on the left is just schematic, right? But these are experimental points, right? When I was a PhD student, I made this diagram, and then I didn't put the points. And my advisor said, you have to put the points, because that shows it's experimental phase diagram. Right?
so what techniques?
Oh, what techniques? Many techniques. So you can use, the thing is, you want to be able to measure something under pressure. That's usually your limitation. But we can measure many quantities under pressure. So you can measure resistivity, electrical resistivity, and then you're going to see a kink at the phase transition, right? So in this case, this material becomes also a superconductor. There is a little region here in yellow that is superconducting. So that was also determined from resistivity measurements. You can measure magnetization under pressure. Okay, it's a little bit harder, but people can do that. You can do neutron experiments under pressure. I'm sure there will be like a lot of talks where you can see like a lot of different quantities that are measured under pressure. And then of course structural. But here it's a magnetic phase transition, so the structure doesn't change. So X-ray studies are not telling you the magnetic phase diagram.
You didn't put any data points on your superconducting.
Yeah, because they would hide the dome. Yeah.
More question?
Yes. So when you're you're talking about the tricritical point,
Yes.
you said that due to singularities on the current surface.
Yes. Yes. So there are theories that well, if you have an itinerant magnet, usually you need to have a large density of states. So that's the Stoner theory. Right? That so you have to have a peak essentially in your density of states, and there are theories that just based on that peak and depending on how sharp it is, can already explain that you're going to have a first order transition at low temperatures. And so yeah, that is like one way to explain this behavior from peculiarities of the band structure. There is another, which is that you still probably have a peak somewhere, but you also have Lifshitz transition. So your topology of your Fermi surface changes. For example, you have 2 pockets and then you have 3 pockets, okay, as a function of pressure. And that also can couple to create a first order transition. Okay? So those theories are good. The one thing that they don't have compared to the other ones, the other two, is that they are less generic. Okay, so magnetoelastic coupling always exists in any material. The magnetization and the lattice couple to each other. And so these scenarios are generic. This works for any metal. As long as you have particle Hall excitation, they are going to couple to magnetization, and you're going to get a first order transition at low temperatures. These ones, they need material specifics. You need to know the Fermi surface shape, you need to know the density of states, and so on. But in a sense, they're also generic, in a sense that to get magnetism in the first place, you have to have those peaks. So,
okay, we better break for lunch. Yes, eat our potato chips.
do we have chips?
I don't know. I don't. Okay, thank you, Valentin. So lunch is ready downstairs. Around 1:30, those are the posters. I'll make an announcement, and we'll go to put up the posters down the road and come back here for 2 o'clock. Okay.